let's start with this thing. Okay, so let me recap what we had done yesterday. Okay. So we'll be considering an operator. So we'll be considering an operator P, okay, to 1, which permutes. So I'm considering here a two-particle system, okay, labeled by, let's say, 1 and 2. Clear? So this is an operator which simply permutes 1 and 2. Okay, so it means that at position 1, you put a state 2, or the state of the particle 2, and at the position 2nd, you put the state 1. Clear? So this is the notation. Okay, so it means, so if you are having, let's say, ui, so this is for the state 1, then you are having this uj for state 2. This is what I had done yesterday. Clear? So what it is doing, it will simply put this uj, this state here, and this state here. Clear? So this is the definition. So it is ui, so uj1 and ui. Clear? And we have shown that this p21, if you act it twice, okay, so on this thing, ui1 tensor uj2, so you will get back. Okay, so let's do this calculation quickly. Okay, so what you will get? So you will get actually, so that means I am applying this twice. Okay, so it means you are saying ui, sorry, uj1 tensor ui2. Clear? So then replace again. So ui1 tensor uj. Clear? So you get back. So it means p21 is equal to identity. What it means? So it means p is its own inverse. Clear? So it means p21 is its own. Got it? Okay. So what are the possible eigenvalues? What are the eigenvalues? So this means, so it means simply p square is equal to identity. So which implies eigenvalues are what? Eigenvalues are plus minus 1. Based on these factors, we will in a moment construct those kind of eigenstates. Okay? Clear? Okay, so before doing that, so we'll show this p21 is a Hermitian operator for a two-particle operator. This thing. So claim is this p dagger 21 is same as what? P2. So it means it's a Hermitian operator. Right? So let's do it. Okay. Okay. So let's do it. What is the definition for the Hermicity in terms of cat and Brown notation? Let's say if you are having for a generic operator, let me take an operator O. Okay. So we define its Hermicity this way. Let's say you are having alpha, then you take O dagger, then you are having beta, it goes as what? Beta O alpha. So it implies then, okay, O is Hermitian. So this is the definition of the Hermicity. I have already explained you in those lectures, supplementary lectures, what I told you. So this is how we define the Hermicity in terms of cat and Brown notation. Now let me take this operator. Okay, so let's write this way. So I will take, since I am in a two-particle system, clear? So that means I have to take this state for a two-particle state system and also this for a two-particle system. Clear? Got it? So that means this vector should be in this two-particle vector space. Okay? So that means, okay, so it means, let me take first this thing. P12, okay? So instead of this beta, I will write, let's say, ui1 tensor uj2. Clear? So this is our two-particle state, and I will apply here again a two-particle state. Let's write that uk1 tensor ul. Clear? Got it? समझ आया? Okay, so let's evaluate this thing. So that means I need to evaluate. So I will evaluate first to the left hand side, then I will evaluate the right hand side and show that they are equal. So if they are equal, that means our O is Hermitian. Clear? So in other words, our P is Hermitian. Okay, so let's evaluate it. Okay. So let's write it. What this will give? So this will be equal to, keep this as such. So UK1, okay, tensor UL2, okay, so let's keep it as such. So, sorry, I have to take P21, P21 is our operator, okay, so you can put as P, okay, but I will keep it as P21, just to remember, I am putting a state 2 at the first place and state 1 at the second place, got it? Okay, so now interchange the states. So this UI will become UJ, okay, and UJ will become clear? Okay, so this will be equal to. So now you are having at first place this object and first place this object. So you take their inner product UK, then you are having UJ. So it's at the first place. Okay, then you are having what? UL. At the second place, you are having UI at the second place. So what that is equal to? Delta Kj, delta Li. Okay? Because they are the vectors in the same vector space. Okay? Now let's take the right hand side now. Okay? So I have evaluated the other way around. So let me take the dagger now. Okay? So let's take the dagger. So this way. Let me take this object UK1. Okay, UL2, okay, so now I will take P dagger to 1, UI tensor, okay, 1 UG, okay, can I take? Okay, so now let's evaluate this thing, what this will give me, okay, so it implies, so I can write it this thing, so I don't know how this dagger acts, because I need to figure out how this dagger acts, clear? So let's try to figure out how it acts. I cannot apply this directly. What I will do, I will take a conjugate of this thing, this way. So I will put this UI here, UI1, tensor UJ2. Okay, so wait a second, what I am doing. Okay, like this thing. P21. Okay, then I am having this object UK1. Okay, tensor UL2. Okay, then I will take a star, conjugate. Is it clear? So if I take the conjugate, this will come here, this will become dagger and this will go there. Okay? समझ आओ? Okay. So now what this object is, I now know how this acts. So it is UI1 tensor UJ2. So what you will get here? So it will be UL at 1 and UK at position. Okay, so now you can write it as, okay, so there is a whole star here. So this UI and UL, so it is UI, UL, okay, at position 1. Then you are having, okay, so UJ and U at position 2. And there is a whole star. So what this is? So everybody has written it? Clear? So now what this is? This is delta IF. Okay? So I can write this as delta IF, delta JK. And there is a star. Clear? So delta is a matrix, identity matrix. So what is a star? It is as such. It will not change it. So it implies this is simply equal to delta IL, delta JK. Now tell me what you get. So left and right hand sides are, they give you the same value. Clear? So what it means? So from, you can call this as first, you can call this as second. Okay? From first and second, you get this P dagger to 1 is same as okay? Clear? Now let's take a consequence of this thing, what it means. Okay. So we have just seen P21, okay, P21 is equal to identity. Clear? Now can I put one of the P2s as P dagger? Because it is Hermitian. So it implies like this, P dagger to 1, P21. So that is actually same as P21, P21 dagger. That's equal to identity. Now tell me, if you are having the matrices satisfying this condition, what you solve? Unitary matrix. If you are having U dagger is equal to identity, or U dagger U is equal to identity, we call those as unitary matrices. So that means this permutation operator, it's a Hermitian operator and it's also a unitary operator. Clear? So in this two particle basis, I am taking only in the two particle basis, okay, so, and showing that it is Hermitian as well as a unitary operator. Clear? Okay, good. So now let's move ahead. So, shall I erase it? Any question till now? Now the point is, let's say if I am having a generic state. Okay, so we have defined here a permutation operator, how to permute between the particles. Clear? Between the two sides, whatsoever you can call. Now I will give a general state. Okay, some generic state for a two particle system. How this permutation acts? Clear? So much, Shaman?
Yes, sir.
So, or does that generic state is an eigenstate of this permutation operator or not? Okay, so we need to figure it out. Okay. So let me take an example. What I mean by that. Let me take some state psi. Okay, alpha. This is our generic state. Beta, gamma minus plus delta minus minus. Clear? So let's act a permutation operator on this thing. So you are having P21 acting on this side. So what it means? So since the first we are saying it is corresponding to 1, this is 1 and this is 2, 1, 2 and so on. I have to interchange the 2. Clear? So let's interchange. So this will be same. There will be no change in the first case. What will be the change? So it will become minus plus. What will happen here? It will become plus minus and this will remain same. Now it is not the same as the psi. Clear? So we don't have the same thing. That means this general state what I am taking here for a two particle system, so it is not an eigenstate of what? This P21. Got it? So much one. But okay, so what we try to do, we try to figure out what are the eigenstates of this P21, which will yield you the eigenstate plus 1 and eigenstate minus 1. Got it? I have shown you P square is equal to identity and its eigenvalues are what? Plus minus 1. So that means I need to construct the eigenstates of this P21. Clear? And this general state is not an eigenstate of this P21. Clear? So now let's try to see how to do it. So there are actually two ways. Okay, so the point is here, this space is a big space. This two particles space, this vector space of the Hilbert space. Let's say you are having this as our two particle Hilbert space that I call V tensor 2. Clear? Got it? So that means there are all the possible number of states existing in this very space. It means there will be only a subset of the states which will be what? Eigenstates of P21. So let me take that one eigenset here, which will be having the eigenvalue plus 1 and another subset will be what? Minus 1. Okay? So if I add the 2, it will not yield me the complete space. There will be other states which are not the eigenstates. Got it? So much, Shaman? Okay, so if I am taking this kind, okay, if you are having a state, when you apply a permutation operator, it gives you the eigenvalue plus 1. What kind of state it should be? So you permute between the two states, clear? So you get an eigenvalue 1. So that means you are getting your state back, because it's an eigenvalue equation. What kind of state it should be? It should be a symmetric state. Okay? In a symmetric state, if it is an eigenstate of a permutation operator, you interchange the two particles, so it will remain same. And another kind of state, if you interchange the particles, so you'll get a change in sign. Got it? So that means you'll be having an antisymmetric state here. Got it? So this subspace will define all the possible symmetric states, and this will give you the antisymmetric states. Got it? So in other words, I can show. I will write. Let me write your symmetric subspace in this two-dimensional. Okay, so this is actually a proper subset of this V2. Okay, and similarly, you are having symmetric, antisymmetric subspace. So this is also a proper set of this thing, this V2. Okay, got it? So much even? Okay, so I will not consider this way. We'll simply directly write the operators for these. Okay. So now let's write. Okay. So let's try to construct these kind of states. Okay. So we define two eigenstates of this P21. Okay, with the following properties. Okay, everybody is getting? Okay, good. So let me take that P21. So I am having a state. Let me call psi s to be one of the states. So it is eigenstate of this P1 with the eigenvalue what? Plus 1. So that is same as psi s. Clear? Okay, so these are the eigenstates of this P. Okay, this P21. And another eigenstate is what? Let me write that as psi a. So it is having an eigenvalue minus 1 psi a. So that's minus psi. Clear? So we call this psi s and psi a as symmetric. So psi s means, so this is a symmetric state. Symmetric under what? Symmetric under permutation. Okay. Symmetric state, and psi a we call what? Antisymmetric. Okay, so these are actually the definitions. And I need to construct what actually psi s is and psi a is. Okay. So is there a way we can turn on these windows? So can you open these windows? Let me define. Okay, so what we need to figure out, how to construct this psi s and how to construct this psi a. These are purely definitions. Okay. So I have assumed psi s to be the eigenstate of this P21 and psi a to be the eigenstate of P21. Clear? With these eigenvalues plus minus 1. Okay, so let me write, let me define operators, two operators. Okay, define these operators. Two operators like this thing. S is an operator. If you define it like this way, half of an identity plus P21. Okay, and another operator A like this thing, half of an identity, you do nothing, and P21. Subtract like this thing. Okay, got it? Okay, so now let's check action of these operators, what they are doing. So much on? So let's try to figure out there, okay, how they act under this P21. Okay, so you can show, okay, so we can have, so if I apply now P21 on this operator S, clear? So let's act it on an operator S. So what it gives me? So half of P21 into identity, it is P21. Then you are having P21, okay, P21. So what it is? So this object is your identity. So it is backward, half of an identity plus P21. So what that is? Your operator S back. So Shaman? Got it? Okay, so if you apply now this P21 on this operator A, what you will get? Half of. So it is P21 minus P21, P21. Clear? So now let's check it. What this object is? It is 1. So you are having minus here. I will take minus out. So it is half of this identity minus P to 1. So what that is? Minus times A. So it means, so S must be an operator which will construct to you a symmetric eigenstate of P to 1. Okay? And A will be an operator which will construct an antisymmetric eigenstate of P to 1. Clear? Okay, so let's do that. Okay, so we can write it this way. Let me take now, so as a consequence of these things, so let me take this state psi. You are having psi as a generic state now, okay? So let me write, okay, for a generic state psi. So a two particle state, and out of this psi, what we need to construct it? The eigenstate of actually P21. And we have shown, okay, earlier, this generic state is not an eigenstate of P21 in general, clear? Okay, and I need to construct an eigenstate of P21 out of this psi, clear? Using which operators? S and A. So let's do it. Okay, so then you can get it. So I will write like this. Let me take S acts on psi. So when S acts on psi, it means it will be a new psi, yeah? Got it? So on that very psi, let me apply this permutation operator this way. So what it means? So it is something P21 S acting on psi. I can write it this way. What is P21 acting on S? So it is S back. Got it? So what does it mean? So what is the value here? It's a plus 1. So it means this S psi, okay, S psi is what? Is an eigenstate of P21, okay, with eigenvalue plus 1. So it implies what? This S psi is a symmetric state. S psi, huh? So you take a generic state and apply S on that, so you will get a symmetric state. I will take an example in a moment, okay? So now let me take this thing now also. This P21 acting on, let's say, A psi. So I should put a cap here. Right? So what is P2? Okay, so I will write it as P21 S acting on psi. So what this object is? It's minus, sorry, it is A, not S. Okay, minus A. Got it? Samajh aawa? So it means A psi is an eigenstate, which implies this A psi is an eigenstate of P21 with eigenvalue minus 1. So it means what? This A psi is an antisymmetric state. Clear? So now let's take an example. Try to construct it. Okay, so let's take a simple example. Then I will take a. So if I am having, let's say, this plus and minus. So our generic state is what? Is it visible?
Yes.
Okay, so let's take our generic state is plus minus. Huh? So that means first particle is in the up state and second particle is in the down state. Clear? Okay. Yeah, as that components. Huh? So now what I need to do? So I need to construct the eigenstates of P21. Eh? Okay, so let's construct it. Okay, construct eigenstates of permutation operator P21 with eigenvalue. Let's say eigenvalue is plus minus 1. Okay, so let me take the plus 1. Which is the eigenstate with the plus 1? S psi. So therefore, okay, for eigenvalue equal to plus 1, I need to construct it. So my eigenstate is what? S psi. Is it? So using this very thing, So now what is our SI? It is half of, okay, identity plus P21. So it will act on this plus 1, size plus minus, clear? So now identity will do nothing, eh? Okay, so it means it is half of, so plus minus, clear? Then you are having plus, what P2 will do? Interchange the two. Now is this a symmetric state? So you interchange plus minus, you will see the first is same as second, clear? So that means it's a symmetric state. So you have constructed a symmetric state, eh? Okay, so now you can check it yourself. Now if you apply this P21 on this thing as psi, okay, so let me write this SI as psi symmetric. Okay, so it means, so let's apply this psi symmetric. Okay, so what you will get? So it will interchange this thing, and that will be same as that. This you interchange, it will be same as this. So it is backward side. So you can show it, yeah? So with the eigenvalue this. Now let me take the eigenvalue minus 1. Okay, eigenvalue equal to minus 1. What I need to do? So you apply a psi. So it is half of identity minus P21. Okay, plus minus. What you will get? It is half of, okay, plus minus. Then you in the middle it will be minus. Clear? Because of this minus. Eh? So you see it's actually an antisymmetric state. Got it? Okay. So now let me give you an assignment. It's simple. Do it. Huh? Okay. So let's say your generic state is psi equal to alpha plus 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 beta plus minus plus gamma minus plus plus delta minus minus. Okay? Construct S psi and E psi. Clear? And show that they have the eigenvalues and show that they have eigenvalues plus minus 1 for P21 operator. Okay? So you need to apply first S. S is your that operate 1 plus. So 1 will keep it as such. P21 will just interchange the things. Then you collect the coefficients of alpha, beta and gamma and delta. Clear? The states coming with alpha, beta and gamma. You will see alpha will be multiplied by plus plus twice and beta will be multiplied by linear combination of plus minus, okay, minus plus. And similarly here, and that will be twice. And you will see it is the same thing. Eh? It will be symmetric. Clear? Now you have got an idea how to construct what? A symmetric state and an antisymmetric state. Okay, out of a general two particle state. Okay, so now let's move to the n particles. Okay, so let's move to the n particles. Have you written it?
Yes.
Okay. You are having now n particle system. Okay. Okay. Now I have to define the way we have defined a permutation operator. Okay, I have to define a permutation operator for what? N particle system. Now let's say you are having n particles at hand. So how many possible permutation will be there? N factorial. Okay? Is that true? Suppose if you you take, let's say, n particles. Okay, you want to permute, let's say, the first element of those set 1 to n. Let's say you permute 1. That means you put it at the all places from 1 to n. How many possibilities? N possibilities. Now take the second. It is having n minus 1 possibilities and so on. Okay, you will get up to n factorial. So the total possibilities are n factorial possibilities. Okay, so it means how many permutation operators I require? I require actually n factorial permutations. Okay, or I require a permutation operator which will induce actually n factorial permutations. I should say like this thing. Okay, okay. So let me write. So let's consider. Okay. So n particle permutation operator. Okay, so there are, I should say, there are n factorial permutations. Okay, so let's write that. Let me write that as p I1 dash 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 in. Okay, so I am saying I1 is the first particle. Okay, and so on. Okay, so I need to figure out an identity here. Identity means doing nothing. So you keep, let's say you are having a set of numbers 1 to n. So you keep it as such. So that means each particle is at its own place, or each number is at its own place. We identify with like this thing, p1 2 dash 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 up to n. So we call as an identity. So by our previous notation, what I mean to say, so you keep the state at the first place and state at the second place. It is as such. You are doing nothing with the state. Clear? Let's say you order the state vectors in your state from 1 to n. Clear? In an ordered fashion. So what does it mean? P1 2. You are doing nothing. So you are keeping the first state at its own place, second at its own place, and nth at its own place. Okay? So that means you are doing nothing with it. Clear? And this operator will give you all the possible permutations of these labels. Clear? Or of these places. Samajh aawa? Okay. So let's take an example. So let's take example of 3 particle case. Okay. So we need. Okay. I will do it. I will put it in a more precise way. Okay. In a moment. Now let me take this kind of thing. Okay. If you are having 3 particle system. So I require actually how many labels? So here are n labels. I require 3 labels. Okay. So for, let me write p. Okay, n p q. So it's a permutation operator. Okay. So for 3 things. Okay, for 3 particles. Let's interpret this thing. This operator. It means, let's say you are having an nth state. Okay. So it means you put the nth state at the first place, and you put the pth state at the second place, and you put qth place at third place. So let me write it. So it means like this way. So it means like this thing. N equal to 1 means nth state move to place 1. Okay. So P, so this is the second position. P means, okay. So pth state move to place second. Similarly, you are having Q at third place. So it means qth state move to place third. Clear? So let's look at how it acts. Let's say if you are having this very state ui, okay, at the place 1, uj at place 2, and uk at place 3. So let's apply this kind of operator. P 2 3 1. So if, okay, so let's look at this thing. So before doing, let's do 1 2 3. This thing. So it's also a permutation operator, is it? So let's look at this very permutation operator. What it will do? It means you keep the first state at its own site, at the first place, second state at the second place, and third state at third place. So it means, so first is this one ui, it will be at its own place. So it is ui simply. So that means it is doing nothing. Clear? So it will do nothing. So it means this P1 2 3, it is an identity. Clear? So that P1 2 to m. Clear? So if I take now like this thing, so if you are having P, okay, 2 3 1, so a non-trivial one. So let's act as this thing. Okay. So what you will get? So what it means? You take the second state to the first place. So it means you will put here. So it is j. So uj at the first place. Then you take third place and put at the second place. So it is uk second place. And then you take the first state to the third place. Clear? So this is how you can do. Okay. So if you remember, okay, we had this kind of thing. P21 for 2 particle system, P21 is equal to identity. Clear? So we had this thing. But here it's not so. You cannot multiply P23 with itself and you will get an identity. Okay? Samajh? So there is a reason. It's a bigger kind of thing. Okay, now tell me, if I am having 3 particle system, how many possible permutation I can have? 3 factorial. That means 6 possible permutation. So a combination of 2 permutations can yield you the identity. 2 different permutations can yield an identity. What does that mean? You take one kind of permutation, then do another kind of permutation. Okay? So that will bring your state back. Okay? It is not necessary. You take first permutation and apply the same permutation, you'll get state back. Clear? Samajh? Okay, so let's clear it here. Okay. So let me take this operation. Okay. So it is P231, the same one, and let me have this thing P312. Okay, so let's apply it on this. So you are having I1 at first place, Uj at second place, okay, Uk at third place. Okay, so let's check. Let's check this. So what you will get? So you are having P231 there. So apply this thing. Third, you need to bring where? First place. So Uk here, and here it is Ui. Second place, and you are having at the third place is the Uj. Clear? So now let's apply this objective. So that means you need to take what is the state at the second place. You bring it where? At the first place. So it is Ui. So at the first place. Now what you are having at the third place, you bring it to the second place. So it is Uj. Okay? Sorry. And what is at the first place, you bring it where? To the third place. So it is UK. It's like this thing. Clear? Is it? So what it means? Now look here. It is equal to. Got it? So there is a reason for why you are having this kind. So this is a different permutation. These two are different permutations. Is it? Samajh? So there is a reason for it. So if you take the set of all these permutations, okay, they form a group. Okay? Got it? So if you take the set of all possible permutations, okay, they form a group under multiplication actually it's a simple operation. Okay, it's an operation, sum operation. Okay, so what I am saying, they form a group. We call that group as SN, a permutation group. It's sometimes known as a symmetric group. So we'll permutation group we'll call it as that. So it is known as a permutation. We'll call it as a permutation group here. Got it? Now if you are having a group at your place, so you take, if you need to define an identity in the group, you take two elements, is it, which are inverse to each other. It's not necessary the same element can be the inverse of itself. Samajh aa? Got my points?
Yes, sir.
Okay, so if let's say if you take only a group of two elements, it's possible element can be actually its own inverse. Okay, but if you take, let's say, the group of more than two elements, okay, a larger group, so it's possible that one element can be inverse of the another element. It's not necessary the same element can be inverse of its own. Okay, got it?
Yes, sir.
Samajh? That is the reason why you need actually a different permutation for this identity. Clear? So it means this P312 is an inverse to this thing, or this is inverse to this thing. Samajh? Okay, so here, what is the order? So how many elements? So what is the n here? It is 3. Clear? So that means this group I call as S3. So how many elements will be there? 3 factorial. So that is 6. So here how many elements? So elements will be n factorial. Clear? Samajh? So now so construct a group of this thing. Suppose I will give a set. Okay, Okay, so let's take this 1, 2 and 3. Okay, just apply the permutation operator. Clear? So how many elements you should get? So once you apply the permutation, that means you put all the possible permutations, distinct permutations. Okay, so you will be getting what? So you will be getting I mean 6 elements. Sir. Okay, so you do like this thing. You put your element like this, 1, 2, 3, and do a permutation. Okay, and take that element, do the permutation, whatsoever are the permutations. Clear? Or you can take like this thing, one permutation, another permutation, something. Okay, so that will be a group having the 6 elements. You'll see that's actually a permutation group. Okay, of order 3. Clear? Got it?
Yes.
Okay. So let's define this permutation operator in more detail. Okay. So, what is this permutation doing? First tell me. So it is okay. So I will give an ordered set. It will put it in a different order, clear? And it will commute simply the elements of that very set. Okay, so it will simply arrange these the ordered set what I am giving in a different order. Clear? It is not necessarily the it will be having the same order as the parent set. Clear? Okay. So in this, okay, so I will define a kind of function, okay. So let's put a simple mathematical definition, okay. So we can define a permutation of n number by a function alpha that maps. Alpha is a function, okay, that maps the standard ordered integers. So I'll be having an ordered integers because you start with the ordered set, and the ordered set means so you are labeling them with the set of integers. You are actually ordering the integers, reordering the integers. Okay. Okay. So this is your standard order of the integers into some arbitrary order, into some arbitrary order, like this. So what it means? So it means you are having this alpha. So it simply orders your this set of integers into some random order. So let's write. So this is alpha 1. Okay. So alpha 2 dash alpha. Okay, got it? So much now? So in other words, you can think this means so all the possible permutations of the 1, all the possible permutation of 2, you can think that way. Okay, all the possible orderings. So it will give you all the possible orderings. Okay. So and S8 and we S8 and S8 with a permutation of like this, right? So I am defining this P alpha is a permutation operator site like this. P alpha 1, okay, alpha 2, alpha. Okay. So this will do simply all the possible permutations. Clear? Defined by how many possible permutations you are doing with this very set. Clear? So they are actually n factorial. Huh? Okay. So let me write. Okay. What this means? So it means with P alpha, if you are having, let's say U1, okay, like this in tensor U2 tensor, okay, dash tensor UN kind of thing. Okay, so that's simply equal to ordering of this very label. So it's alpha 1 like this thing. Okay, U alpha 2 dash U alpha. Okay. समझ आओ? So let's take the example of okay 4. Everybody has followed it?
Yes, sir.
Okay. So you can check. Okay. check for like this thing. So if you are having P3142, so that means you are having 4 particles. Okay, so let's say you are having U1 like this thing at 1, U2 at 2. Okay, so you are having that in state at third will come at the first place. So U3 will come here. Huh? You can do this kind of permutations. Okay, so it's now simple. Okay, so let's stop here. Shall we? There are 2 more minutes. Huh? Yes. Okay, so let's finish this topic. This you have got. It is the same idea what we have done for the 2 particles. I am going to where? The n particle case. Okay, ultimately we are actually interested only in the symmetric and the antisymmetric case because they turn out to be the eigenstates of this permutation operator. Clear? Okay, so if you see, okay, all these permutations, if you take any kind of permutation, okay, they will not commute with each other. So that means you are not able to figure out the simultaneous eigenstates of these permutation operators. So there will be only the set of permutation operators which will either symmetrize or anti-symmetrize. Okay? So only in that very case you will be having the permutation operators commuting with each other. Got it? Okay, so let's try to construct this symmetric and anti-symmetric case for the n particle system. Okay? Okay. So let's take, okay, consider n particles. So you people are following what I am writing here? So you have followed that definition, eh? Okay? Okay. Each with same vector space. Same vector space. Clear? So I will take this P alpha, be an arbitrary permutation. So I will take an arbitrary permutation. Okay? Then I define, okay, the symmetric state. This psi s, okay? So I will define the symmetric state psi s in this way. So you active this P alpha on psi s is equal to psi s. Clear? For all alpha. So because these are all the possible n factorial permutations, is it? Under all those permutations, it should remain same. So the same thing, P21 acting on psi s gives you psi s. Clear? And now if I am having an antisymmetric state, okay, let's call that as a psi a. So I will act with this permutation operator this way. Okay, so what should I get? What I should get? So if I act P alpha on psi a is an antisymmetric state. What should I get? So now here is a catch. So let's say if you are having 3 particles, clear? So you can do with these 3 particles either the even number of permutations or the odd number of permutations. What does that mean? You can permute 3 particles simultaneously. That means how many you count? 2 permutations. Let's say 1, 2, 3. You replace 1 by 2, 2 by 3. Clear? So this is one permutation. Or it is possible you keep one particle fixed and permute the other 2. So that carries only the odd permutation. Clear? So let's say if you are having 4 particle system and you want to do the permutations, how you can do? You can do in the odd ways as well as the even ways. Okay, here it doesn't matter. Okay? Got it? Because there is no sign change. I don't want any kind of sign change. But here the problem is, let's say you do an odd permutation, that means you just replace one particle by the another. So you should get a sign change. But if you do the simultaneously the second particle by the third particle, let's say, that means 2 permutations in one go. So what you should get? Minus and minus, that is plus. So that means if you are having odd permutations, you will get a minus sign, and if you are having an even permutation, you will get what? Positive sign. Okay. So let me introduce here epsilon alpha. Okay, psi a for all alpha, and this epsilon alpha is actually called +1 if even permutations. So I will give an example: -1 if odd permutation. Okay. So, okay, I will give an example. Now we need to define an operator which will create your symmetric state and an operator which will create what? Antisymmetric state. Clear? Okay, so let's write those operators, then we'll take an example. So operators will be, so let me write this symmetric operator. So how many possible permutations? N factorial. So divide that by n factorial. So sum over all possible permutations, because alpha is a permutation, is it? Okay. So you apply now. What should be here? What should be here? P alpha. P alpha is a permutation, and you sum over all the possible permutations. We call this operator as symmetrizer. So this operator symmetrizes your state. And then you are having this A, so I will define it by like this thing, 1 by n. Okay, so let's define them this way: summation over alpha, all the possible. Now you are having P alpha, and there will come this, whether they are odd in number or even in number. Okay, so I will put an example. Okay, so this epsilon alpha. So that is why you will get a minus signs with certain terms. Okay, so this is a very general definition. Okay, let's go to the two particle case. Clear? And figure out the operator what we have defined for two particle case. Does we get it from these or not? Clear? So let's take it. So I am almost done. Huh? No issues. Okay, so let's take two particle case. Now tell me what are the permutations? Okay, so if I am having two particle case, my permutations will be P12 and P21. So what this means? It means you do nothing. Clear? And this means you interchange what? 2 by 1 or 1 by 2. Clear? Now let's write this S. So what will be n factorial? 2 factorial. Okay, sum means all the possible permutations. You are having only two permutations. You will write then P12 plus P21. So what this P21 is? P12, it is identity. So it's 1. So this is an identity plus P21. Okay, so this is actually identity. Okay, so now let's look at A. So what you will get? 1 by 2 factorial. Okay, so first is P12. Clear? Now look here. How many? Is it an odd permutation? So you are making only one change. Clear? So it is an odd permutation. What you will get for epsilon alpha? You will get a -1 P21. Got it? So you are having here only one permutation. So it is 1 by 2. P12 is identity minus P21. So it is the same thing what we had defined earlier. Okay? Okay, so now let's take three particle case quickly. Okay, so that then we'll stop. Okay? Any question? Okay, so now let's, have you written it? Okay, just write it. Let me take n equal to 3. So that means 3 particles. So let's count what are the possible permutations. Okay. So first permutation is what? So 1, 2, 3. P1, 2, 3. Clear? So let's do it. So this will be simply identity. Is it? So you are doing nothing with the system, with your ordering. So you can say 1, 2, 3. These are your particles. Okay, so the next is like this thing. P, so do it in the cyclic order. P, 3, 1, 2. Clear? Then again, P, 2, 3, 1. Clear? Okay. So now, then you can be having P, 1, 3, 2. Okay, then you can be having P213, then you can be having what? P321. So much, Aman? So these are actually cyclic, these are not cyclic. Got it? Okay, so now let's look here. Okay, so let's take this S first. So therefore S is equal to 1 by 3 factorial. Okay, the sum of all possible permutations. So these are the possible permutations. So this is identity plus P312 plus P231 plus P132 plus P213 plus P321. Clear? So this is quite straightforward. Now let's look at this A. So what that is? 1 by 3 factorial, that's equal to 6. So I will write 3 factorial. So identity. I need to actually look at even and odd permutations. Clear? Now let's look at here. So, okay, this is okay. This is an identity. Nothing. Now let's look at whether this is an even or odd. Okay, if you see, you have actually this two permutations done simultaneously. How?
1, 3.
So 1 and 3 and okay. So 1 and 3 and 2 and 1. Clear? Rather 2, 3 and 1, 2. Okay? Samajh? So you are having 1 and 2 and then 2, 3. So that means it makes two permutations. Okay? So similarly you are having these as two permutations. Now let's look at this thing. So what you are having? One is fixed, first place is fixed, only second are interchanged. So this is an odd permutation. Clear? So what about this thing? 3 is fixed. Okay, so this is an odd permutation. What about this thing? Odd permutation. So I will write this as odd. So these are odd permutations and these are what? Even permutations. Clear? So in other words, if you can, okay, so you can put it this way. If you are not able to figure out whether these are even or odd, just take the cyclic terms as what? Even, and the non-cyclic terms what? Odd. Got it? So what I need to do? So put a plus sign because epsilon alpha is plus 1 for even. Okay? So I'll put it like this. P312 plus P231. Then with the odd permutation you put a minus. So it is P132 minus P213 minus P3. So this is a symmetrizer for the 3 particle state and this is the anti-symmetrizer for what? 3 particle state. Okay? So just apply on this thing. Okay? So I will give you a 3 particle state. Clear? So let's take a 3 particle state simple. Simple. Yes. 3 particle state like plus, let's say plus, minus. Okay? Got it? So I am giving you the state psi is equal to this thing. And you need to make it symmetric as well as antisymmetric. Got it? Samajh? Okay. So just apply S and A on it, you will get a symmetric state or antisymmetric state. Okay? So that's it. So if you